Later in the semester, we're going to talk about parallel database systems and big data, and how we can use multiple computers to solve problems for very large data sets. This is all part of scaling up database systems to large environments like the cloud or big data centers. Today, however, we already have enough tools to understand how parallelism would work for these core algorithms of hashing and sorting. And it's very natural because really what we're going to do in a parallel system is very similar to the way that we use memory for our divide and conquer techniques in the out-of-core algorithms we've seen. So let's see how this goes. We'll begin with hashing. And what we're going to do in these pictures is we're going to represent multiple computers connected by a high-speed network. So you can imagine that the rectangle and can that's on each row of this picture is a computer. Okay, so there's three computers here, each of which has a memory, the rectangle, and a disk, which is the can. And because these computers are connected by networks, we can read from the disk of one computer and send it to the memory of another computer. Okay, so the arrows represent the ability to send data from a disk on one computer to the memory of another computer. Okay, and so what we're going to do is we're going to introduce a new hash function, a third hash function, h sub n, and it's modulo the number of computers in the network. So h sub n will produce one of the indexes or IDs of the computers in the network. And as we scan the data, we're going to ship it to the appropriate computer based on the value of h sub n. We do this as it streams out of the disk. And so when we look at a disk block, we're going to decide which machine the record should go to and send it there. So in this schematic, we're showing the data coming directly from the disk drives. In fact, it would come from the CPU of the computer that was doing the scan. Okay, so this independent hash function hn is going to partition the data across the machines. When we're done with this phase, if two records are the same, it means their hash value is the same and they are on the same machine after this first hashing phase. Once you have them on the same machine, the rest of the algorithm is just what we learned so far. Basically, on that machine, you take the data as it streams in and you partition it using h sub p into partitions, and you store it on disk. And then, of course, in the conquer phase, you pick up each partition and you put it in a main memory hash table and you send it to the output. Looking at this picture, you'll see that we do one scan on the far left of the entire data set in parallel across all the machines. So all those disks are scanning at the same time. And then in the middle, we do one pass of the data to write it across all the machines in parallel to generate these partitions. And then we read from all the machines in parallel to do the local reads into the hash tables. And then we write across all the machines in parallel to write out the hashed runs. And in total, we're still doing 4n IOs, 2n for the first phase and 2n for the second phase. So the IO cost is the same, but of course that IO is now parallelized across the n computers, in this case 3 computers, that we're working with. And so it goes n times faster for a number of computers n. And so that's the simple way to parallelize hashing. It's really very simple. We just introduced a new hash function for network partitioning. And as we scan the data in the first phase, we partition it across the network.